Nearly 31 feet of driving wheelbase locked rigid in a single frame. No hinge, no pivot. 12 driving wheels aimed down a railroad full of curves. By every principle of locomotive engineering in the 1920s, this machine should not have worked. It should have wrecked itself on curves, eaten through its own bearings, and spent more time in the shop than on the road. Instead, 88 were built, and they ran for nearly 3 decades. This is the Union Pacific 9000, the longest non-articulated steam locomotive ever built. And understanding how this unconventional machine somehow worked begins with a freight crisis no conventional engine could solve. In March 1926, the American Locomotive Company, or Alco, completed the prototype of a design that defied standard railroad practice, the Union Pacific 9000 class. This locomotive featured a 4-12-2 wheel arrangement, a 4-wheel leading truck, 12 massive driving wheels coupled together, and a 2-wheel trailing truck beneath the firebox. It was a singular American design choice. While some European railroads experimented with 3-cylinder power on shorter wheelbases, no other North American carrier ever ordered or built a 4-12-2. This engine represented the extreme limit of rigid frame technology, pushing the physical length of non-articulated steam power to its absolute boundary. To fit 12 67-inch driving wheels onto a single, unbroken steel frame required a rigid wheelbase of exactly 30 feet 7 inches. Standard engineering logic dictated that such a long, unyielding wheelbase would bind on curves, tear up track, and derail under normal operating conditions. Yet Union Pacific and Alco did not design this machine as an experimental novelty. The first engine, road number 9000, officially rolled out of the shop on April 8, 1926, to serve as a fast, heavy workhorse. The partnership between the railroad's mechanical department and Alco's design staff produced a locomotive that relied on an inside third cylinder to distribute piston thrust across the massive frame. The 9000 class was built to test whether precision engineering could overcome the physical laws of track curvature, proving that a rigid frame giant could conquer the main line. The justification for this massive machine lay in the demanding operational reality of the Union Pacific Main Line. By the mid-1920s, the railroad faced a severe freight bottleneck across its flatland corridors in Nebraska and eastern Wyoming. Tonnage was surging, and the existing fleet of 210-2 Santa Fe types and 2880 consolidation Mallet locomotives was struggling to keep pace. While these older engines possessed plenty of raw pulling power, they were limited to a grinding 20 miles per hour. On a competitive transcontinental route where time meant money, drag-era speeds were no longer acceptable. Moving heavy trains was only half the challenge. The railroad had to move them quickly. Union Pacific's strategic goal shifted from maximizing tractive effort at low speeds to achieving high sustained velocities with massive payloads. This meant finding a locomotive that could handle a mile-long, 120-car train and maintain 50 miles per hour across hundreds of miles of relatively flat mainline track. Freight velocity mattered just as much as pulling capacity. Articulated locomotives of the era were not yet the fast, modern machines they would later become. The early Mallets suffered from stability and hunting issues at speed, and their fireboxes were relatively small compared to their overall boiler size, which restricted their sustained horsepower. The railroad needed a completely different approach. Union Pacific's mechanical department drafted an operating brief that demanded a combination of speed, stability, and tractive power that no existing locomotive class could deliver. The operational demands of the overland route shaped the blueprint, leaving the railroad with a high-stakes choice. Accept the limitations of slow freight, or build something entirely unprecedented. To solve the speed and tonnage problem, Union Pacific first assessed the standard heavy haul option of the era, the articulated Mallet. In theory, These machines offered the perfect blueprint. By splitting the driving wheels into two separate hinged engines under one boiler, an articulated locomotive could distribute its immense weight and negotiate tight mainline curves with ease. On paper, they delivered massive tractive effort. In practice, the 1920s articulated designs failed the speed test. The very mechanism that allowed them to curve, the articulated hinge, created severe instability when pushed beyond low drag speeds. At speeds exceeding 25 miles per hour, the front engine unit began to oscillate violently from side to side, a dangerous lateral instability known as hunting. This hunting behavior caused extreme wear on both the track and the locomotive frame, making high-speed operations a massive safety hazard. Furthermore, the compound steam technology utilized by older Mallets restricted performance. These engines recycled steam from high-pressure cylinders to larger, low-pressure cylinders. At higher speeds, the massive low-pressure pistons could not move steam out of the cylinders fast enough, causing back pressure that choked the engine. The locomotive simply could not breathe when running fast. Compounding the issue, early articulated designs suffered from restricted boiler and firebox proportions. The physical constraints of mounting a single boiler over two pivoting engines limited the size of the grate area. Without a sufficiently large firebox, the locomotive could not generate enough steam to sustain high horsepower over long distances. The articulated fleet was highly capable of dragging heavy tonnage up mountain passes at a crawl, but it was physically incapable of maintaining 50 miles per hour across the Nebraska plains. Union Pacific had to look elsewhere. The American Locomotive Company approached Union Pacific's speed and tonnage problem by rejecting the prevailing logic of articulated design. Rather than trying to stabilize a hinged locomotive at high speeds, Alco's engineers proposed an audacious alternative: a single, unbroken rigid frame carrying 6 coupled driving axles. This design eliminated the pivoting hinge entirely, removing the primary source of dangerous lateral oscillation that plagued early Mallet engines on fast runs. Choosing a rigid frame architecture meant Alco could design a massive, highly efficient boiler that did not have to flex or accommodate leaking steam joints. High-pressure steam could flow directly from the superheater to the cylinders through short, straight pipes, minimizing pressure drops and allowing the locomotive to breathe freely at 45 and 50 miles per hour. Furthermore, a single, continuous frame provided a stable platform for a massive firebox, which could generate the continuous steam volume required for sustained high horsepower output without restricting draft or combustion. Alco's design prioritized a long, rigid wheelbase over a pivoting frame. By coupling 6 driving axles together in one rigid frame, they distributed the locomotive's weight across 12 67-inch drivers, maximizing rail adhesion without sacrificing stability. A longer frame acted as a natural stabilizer at speed, tracking straight and true where articulated engines hunted violently, keeping the massive machine stable on the high-speed main line. But this architectural choice presented an immediate physical challenge. A rigid wheelbase spanning 6 coupled axles would measure over 30 feet, an unprecedented size. No North American railroad had ever attempted to run a rigid frame locomotive of this length in regular service, as standard engineering principles warned that such a machine would inevitably bind on curves and destroy track. Alco was betting that precise mechanical engineering could overcome these physical limits, offering a high-speed, high-tonnage solution that bypassed the mechanical complexities of articulation. To extract maximum tractive power from a rigid frame without exceeding the tight clearance limits of the American railroad network, Alco's engineers could not simply make the outside cylinders larger. Doing so would make the locomotive too wide to clear platforms, bridges, and tunnels. Instead, they chose a rare and demanding alternative. They split the power among 3 cylinders. 2 conventional cylinders, measuring 27 by 32 inches, sat on the outside of the frame in the usual position. The third cylinder, measuring 27 by 31 inches, was buried out of sight, cast directly into the center of the heavy cylinder saddle between the locomotive's steel frames. This hidden cylinder did not sit level. To allow its heavy connecting rod to reach the driving wheels without striking the first axle, engineers inclined the center cylinder upward at a 9.5-degree angle. This diagonal orientation raised the cylinder axis 9 inches above the level of the outside cylinders. Further clearance was carved out through the engine's physical spacing. The first axle was entirely straight, carrying no crank, to let the inside connecting rod pass safely over it. The distance between the first and second driving axles was stretched to 88 inches, 18 inches wider than any other axle spacing on the frame. The true mechanical heart of this arrangement was the second driving axle. Unlike its straight companions, this axle was forged with a heavy, offset crank. It functioned as a massive crankshaft, receiving the direct diagonal thrust of the inside cylinder's piston rod. With 3 cylinders firing at balanced intervals, the locomotive produced an incredibly smooth power stroke, generating 4,750 horsepower and over 96,000 pounds of tractive effort. Power was distributed across the massive frame, reducing the immense stresses that would have torn a 2-cylinder rigid frame apart. Alco had successfully packed the muscle of a giant into a standard physical clearance, but they had done so by burying a highly active, heavy engine block inside a dark, inaccessible steel frame. Controlling the steam flowing into this buried third cylinder required a radical departure from standard design. On a conventional locomotive, each cylinder relies on its own dedicated set of moving rods and links, the valve gear, to precisely time the admission and exhaust of steam. The Union Pacific 9000 utilized standard Walschaerts valve gear on its 2 outside cylinders. However, adding a third complete set of Walschaerts gear inside the frame was physically impossible. The space was already crowded with the inclined center cylinder, its heavy connecting rod, and the massive cranked second axle. To solve this spatial puzzle, Alco and Union Pacific licensed a design from British engineer Sir Nigel Gresley. His conjugated valve gear was a brilliant application of mechanical geometry. Rather than building a separate independent valve gear for the inside cylinder, Gresley's system derived the necessary motion directly from the 2 outside valve sets. The physical mechanism consisted of 2 heavy steel levers mounted horizontally across the front of the locomotive frame, just ahead of the cylinders. One long lever pivoted on a central bearing, while a shorter lever attached to it. These levers linked the valve spindles of the left and right cylinders directly to the valve spindle of the center cylinder. As the locomotive ran, the outside Walschaerts gears drove the outer valves in their normal cycles. The levers mechanically calculated the difference between these 2 motions in real time. Because the 3 cylinders were timed to fire at equal intervals, the mathematical sum of the left and right valve movements perfectly matched the exact timing needed for the center valve. It was an incredibly elegant piece of engineering. The outside gears did double duty, eliminating the weight, cost, and physical footprint of a third valve gear. This was a rare and highly ambitious North American application of Gresley's concept, transforming a complex clearance problem into a simple matter of leverage and mathematics. The physical barrier of track curvature stood as the last major hurdle. A rigid frame holding 12 driving wheels over a span of 30 feet 7 inches could easily bind on standard mainline curves, grinding against the steel rails and risking immediate derailment. To force this giant around curves, Alco did not try to make the frame bend. Instead, they engineered controlled play directly into the running gear. They equipped the first, fourth, and sixth driving axles with lateral motion devices. These specialized axle boxes allowed the steel wheel sets to slide sideways within the frame, providing up to 2 inches of lateral play on the outermost drivers. To complement this side-to-side movement, the fourth set of drivers was originally built flangeless. By removing the steel flange on this middle axle, the wheel could slide across the top of the rail on sharp curves without binding against the inside edge. Though Union Pacific later added a small, shallow flange to these blind drivers to improve tracking, the lateral motion devices gave the long wheelbase just enough flexibility to traverse mainline curves of up to 7 degrees. This setup meant the locomotive did not need unlimited flexibility. It needed just enough calculated movement to accommodate the physical limits of the overland route. On real track, the rigid frame concept survived because of this practical running gear design, proving that precision tolerances could make a 30-foot rigid wheelbase workable on standard rails. In March 1926, the prototype locomotive, road number 9000, arrived on the Nebraska Division to begin immediate road testing. The engineering worries of track damage, binding, and derailments vanished during the first runs. Running over standard mainline rails, the massive rigid frame giant successfully navigated 7-degree curves and demonstrated an exceptionally smooth ride at speeds that had previously caused articulated mallets to oscillate violently. The real payoff of the design lay in the daily operating logs. The 9000 class transformed operations across the flatland corridors. In regular service, these 3-cylinder locomotives routinely hauled mile-long, 120-car freight trains at 50 miles per hour, occasionally touching 60 miles per hour on level track. With 4,750 horsepower, 96,646 pounds of tractive effort, and 354,000 pounds of weight resting directly on the driving wheels, they delivered passenger train speeds with heavy tonnage payloads, solving Union Pacific's freight bottleneck. This performance validated the high-stakes engineering gamble taken by the railroad and Alco. Union Pacific bypassed any hesitation over the prototype and immediately committed to the design. Later in 1926, the railroad took delivery of 14 additional units, designated Class UP2, numbered 9001 through 9014. 3 subsequent production batches, built between 1928 and 1930, expanded the fleet across 5 distinct subclasses, UP1 through UP5. By 1930, the total had reached 88 locomotives, with units assigned to the parent railroad, as well as its Oregon Short Line and Oregon-Washington Railroad and Navigation Company subsidiaries. These 88 locomotives became the undisputed workhorses of the transcontinental main line between Council Bluffs and the Rocky Mountains. They proved that a rigid frame locomotive with 12 coupled drivers could handle the demands of high-speed, heavy freight service on an unprecedented scale. Before the first diesel-electric units or modern, simple, articulated locomotives arrived to challenge them, the 9000 class had already established itself as a practical, highly effective answer to Union Pacific's speed and tonnage problem, proving on everyday rails that this unconventional machine worked. The moment a 9000 class locomotive rolled off the main line and into the bustling shop bays at Cheyenne or Omaha, the triumph of its high-speed performance met the grim reality of its design. The very arrangement that allowed the engine to conquer the Great Plains, the packing of 3 power plants into a single rigid frame, exacted a heavy toll from the men tasked with keeping it alive. The heart of the problem lay in physical access. On a conventional 2-cylinder locomotive, nearly all moving parts are hung on the outside of the frame, fully visible and easily serviced by a mechanic standing on the shop floor. On the 9000 class locomotive, the 3rd cylinder, its piston, and its massive connecting rod were buried within the dark, grease-slicked confines of the steel frame, directly beneath the boiler. To inspect or lubricate these components, a machinist had to climb into a cramped, tight space working in near-total darkness surrounded by hot metal and dripping oil. The cranked second axle was a particular source of frustration. Because this single piece of forged steel received the direct diagonal thrust of the inside piston, it wore rapidly. Regrinding and remachining the offset crankpin journal required major disassembly of the driving wheelbase, a process that kept these engines in the shop far longer than standard locomotives. The inclined mounting of the center cylinder also introduced uneven physical forces. Because the cylinder sat tilted at a 9.5-degree angle, gravity and piston thrust caused the heavy piston head to drag along the bottom of the cylinder wall. Over time, this produced severe, asymmetrical scoring on the cylinder liner, forcing shops to frequently rebore the cylinder and press in new liners. These issues split the locomotive's upkeep into two distinct competing schedules. While the conventional outside running gear followed a standard 12,000-mile overhaul interval, the internal machinery demanded a complete annual teardown just to inspect the inclined rod bearings and lateral motion devices. Clever engineering had squeezed immense power into a rigid frame, but the cost was a permanent, labor-intensive friction on Union Pacific's maintenance system. The Gresley conjugated gear relied on a series of pins, levers, and bearings to mathematically calculate the position of the center valve. When freshly machined, the system worked with geometric precision. But on the main line, under the relentless pounding of heavy freight service, tiny amounts of play began to develop. Each pivot and bearing in the horizontal levers experienced constant alternating forces. A fraction of an inch of wear at a single joint multiplied as it traveled through the linkage. This physical wear did not trigger a sudden, catastrophic breakdown. Instead, it introduced a gradual, systemic timing drift. As the pivots loosened, the mechanical calculations performed by the levers degraded. The real danger of this mechanical drift emerged at speeds above 45 miles per hour. The cumulative slack in the worn linkage caused the valve of the inside cylinder to travel further than designed, a phenomenon known as valve overtravel. With the valve opening wider and remaining open longer, the inside cylinder was fed an excessive volume of steam. Instead of sharing the workload equally, the hidden middle cylinder began to overrun. It pulled more than its share of the load, throwing the three-cylinder balance out of alignment. This imbalance produced uneven power strokes, subjecting the cranked second axle to violent, asymmetrical stresses and causing the entire locomotive to vibrate. While Union Pacific later retrofitted roller bearings to some units to combat the wear, they could not bypass the physical limits of the design. The timing drift established a practical ceiling for the 9000 class, the very mechanism that made the three-cylinder rigid locomotive possible. Also guaranteed its performance would degrade with every mile it ran. The ultimate measure of any locomotive design success is its adoption by the wider railroad industry. When an engineering layout succeeds, other carriers copy it, adapt it, and order it in volume. Yet, as the 88 locomotives of the 9000 class ran on Union Pacific's flatland main lines, the rest of North American railroading watched and chose a different path. No other American carrier ever ordered a 412-2. The wheel arrangement remained exclusive to the Union Pacific system and its subsidiaries. For rival railroads, the engineering trade-offs of the design were too extreme. Union Pacific possessed the long, straight stretches of the overland route where a 30-foot rigid wheelbase could run freely. Most other railroads operated on tighter curves and steeper mountain divisions, where a locomotive requiring specialized lateral motion axle boxes just to stay on the rails was a constant liability. The mechanical departments of rival lines also rejected the high price of three-cylinder power. The buried middle cylinder, the vulnerable cranked axle, and the high-maintenance Gresley valve gear were notorious shop floor headaches. For most railroad operators, it was far more practical to build standard two-cylinder locomotives with shorter wheelbases than to adopt a machine that required specialized annual teardowns. The 9000 class became an evolutionary dead end. It was a highly specialized tool built for a single geographic corridor, rather than a design template for the future of steam. The locomotive's historical significance rests on this isolation. It demonstrated that precise mechanical engineering could solve a specific operational bottleneck, but it also proved that the solution was too complex and costly for the rest of the industry to copy. In 1936, the American Locomotive Company delivered a new locomotive class to Union Pacific, that fundamentally changed the mathematics of high-speed freight. This was the 4664 Challenger, a simple articulated design that solved the speed and tonnage problem without the severe compromises of the 9000 class. By splitting the driving wheels into two independent pivoting engine sets under a single boiler, the Challenger eliminated the massive 30-foot rigid wheelbase. More importantly, it achieved this flexibility without the hunting and stability issues of earlier Mallets. Equipped with 69-inch driving wheels and conventional outside-mounted Walschaerts valve gear, the Challenger could easily sustain speeds of 70 miles per hour. It matched the 9000 class's 96,000 pounds of tractive effort, yet did so with a fraction of the maintenance burden. There were no buried center cylinders, no cranked axles, and no delicate conjugated levers to fall out of alignment. With the Challenger, Union Pacific possessed a design that could handle the overland route's tonnage without the high shop floor costs. The railroad ultimately purchased 105 of these articulated engines, which steadily took over the premier fast freight runs across the system. While the Challenger proved that modern articulation was a superior mechanical path, a far more disruptive technology arrived in 1940. The introduction of the Electromotive Division's FT diesel-electric locomotives made the entire maintenance-heavy logic of steam power obsolete. Though a single early diesel unit generated only 1,350 horsepower, railroads could couple multiple units together under the control of a single crew. Diesels did not require massive water treatment facilities, complex valve alignments, or specialized annual teardowns. They delivered high operational availability and reduced fuel consumption. By the early 1950s, diesel-electric power achieved a 15 to 20% improvement in Union Pacific's operating ratio, making even the most efficient steam engines economically non-viable. Modernization overtook the 9000 class not through a dramatic mechanical defeat, but through the quiet calculation of railroad economics. The 88 locomotives of the 9000 class were steadily displaced to secondary roles before being withdrawn from service entirely. By April 1956, the last active 412-2 retired from the Union Pacific roster, bringing a close to an ambitious engineering compromise that had run its course. Today, the last surviving 9000 class locomotive stands silent, a monument to daring compromise. It reminds us that progress is rarely a straight line of clean victories. Real innovation is messy, demanding complex trade-offs. As modern engineers confront their own limits, the ultimate lesson remains. Sometimes the most valuable breakthroughs come from the bold anomalies that defied the rules, and somehow worked. What do you think of this machine's legacy? Let me know in the comments.